Okay, thank you very much, Martin. Thank you very much for introducing me. So I want to start by saying that it is indeed the last talk of this spring school. And during this spring school, you already had, several talks on the topic of stochastic topology, which I also will represent in. Can you hear me? In my talk. So you heard talks by Benarus about random Morse functions. There was a talk of Ginestra Bianconi about networks, large random networks, and there was a talk of Erdős-Rényi about high-dimensional expanders. So my talk will be different, but I mean, there's all directions, all these four talks, including mine, they kind of represent different, very different sides of the subject, which is called stochastic topology. So my title is Topology of Large Random Spaces, and maybe I'll start by making a definition of what is a large random space. The definition is informal, but it kind of describes some typical properties of the spaces. So I stated it like this. A large random space is a topological space, typically a simplicial complex or a manifold, which is the product of many independent random choices. So we will see in this talk, different models where all these properties are satisfied, that we have large random spaces of different nature, of different character, but they all have this in common, that they are created by many, many independent random choices, which is described in this definition. So the situation here is a little bit similar to what happens between the classical mechanics and the statistical mechanics. These are two different theories, which are very different, but they don't contradict each other. They kind of support each other and kind of live independently. And they are valid in different, under different assumptions. So classical mechanics is when we have a small system with, let's say, a few particles or a number of particles, or a machine which we can describe fully, and we can write initial conditions for the system, and we have equations of motion, and then we can integrate these equations, at least in principle, and this is what classical mechanics is about. So, example are this planet system and solar system, movement of planets. Statistical mechanics is a very different subject. So here one deals with systems consisting of millions of different particles. And in this situation, it's like a gas, like air in the room. So in this situation, you cannot hope to describe the system fully. There is no way you can say the initial condition is given by a certain vector. So, but nevertheless, statistical mechanics gives very useful, very precise predictions, and kind of uses completely different notions like pressure, temperature, entropy, and so on. So we see that these two theories are completely different, but there is no contradiction between them. So what we want, this deterministic topology is the usual topology which we know from all the books, when the spaces are given precisely, and we want to have stochastic topology, some subject which kind of a dream of many people in this room in particular, many mathematicians trying to create this subject, what are large random spaces? What is stochastic topology? And of course, there are many, many different answers, and some talks of this conference provide completely different approaches, which is okay, which is fine, which is normal. So one reason for are you impressed? Okay. So one motivation to study large random spaces comes from the theory of complex networks, and we had very nice talk, lecture, 2-hour lecture by Ginestra Bianconi yesterday. So I just briefly mention here basic notions here. So the standard way of representing a network is by using graphs. So a graph has vertices and edges, and vertices represent some objects, and edges represent relationships between objects. So this is a usual standard way of representing networks. However, actually, Ginestra also made a big emphasis on this, that in many situations there is need to use simplicial complexes instead of graphs. So the simplicial complexes has an extra structure than additional to graphs. You can say that 3 objects have some collaboration or some relationship between them. So there can be relationship between not pairs of objects, but between triples of objects. And if you have triple of objects, you can represent it by a triangle in your simplicial complex, or you can have even bigger relationships between a bigger number of participants in a relationship. And here I have a very simple example. When you have I should admit I don't know much about this, but market transactions are characterized by a buyer, seller, and a broker. So there are 3 participants involved. And I have another example here, which is familiar to people in this room, MassSignNet. So MassSignNet is a database of mathematical authors. So we have nodes are represented by mathematicians, all of us, and we can view it as a simplicial complex. So we can say we can connect 2 authors. So we take all authors as vertices of our simplicial complex, and then we connect 2 authors if they have a common paper. But there are papers which are shared by 3 authors, so then we should put a triangle there, connecting the 3 authors, and so on. And so we obtain a simplicial complex, and there is a question: what is the dimension of the simplicial complex, which means what is the maximal number of authors in a mathematical paper? So it's still an open question. So if you look at this MassSignNet, it is a finite and deterministic, so it is kind of, it's not what we want. I mean, it is not large. I mean, I will describe what it means large a bit later. And it is not random, it is deterministic. I mean, it's given. You can just log in and you can see. But it is large. It is so big that we can view it as being random. We can apply to it kind of statistical properties. We can say, what is the probabilities? How many authors in general have a paper? What is the degree of an author? How many joint papers he may have with other people, and so on. So we can apply statistical methods. So this my talk and some results from this talk could be in principle used for understanding the small net. So my talk will be more mathematical. So I'm trying to kind of understand what are mathematical foundations of the stochastic topology, what are models of random manifolds, large random manifolds and large random simplicial complexes. And we will see many examples in my talk. So besides that, we will see that we can use this stochastic methods to tackle some open conjectures from deterministic topology, the Whitehead conjecture and Eilenberg-Gonnet conjecture. So I will speak about in my talk. So maybe I'll just before we start this, I want to say that there's two properties, large and random. They are very important together. They complement each other. So if you just say random, you can, well, anything you can be random. But if it is large random, then there are some special effects coming, and they are similar to the central limit theorem in probability theory. When you sum up many independent random variables, you can predict the result. I mean, the result becomes very predictable, and this the error which may occur tends to zero when some parameter goes to infinity. So these two properties, large and random, very well complement each other, and the answers we get are, well, with probability nearly 1, probability tending to 1, and I will explain what it means. So, so in this talk I will mention several models. We'll start with random surfaces, random three-dimensional manifolds, random configuration spaces, random simplicial complexes, the Linial-Meshulam model, random spherical two-dimensional complexes and those conjectures, Whitehead and Eilenberg-Gonnet conjectures. I will speak about the multi-parameter random simplicial complexes, and there will be some conclusions. Okay. So let's, I will go rather quickly through three first topics. I just want to mention them briefly just to give you an idea. So we'll start with random surfaces. So this was developed by Pippinger and Schleich, was published in 2006, and this model is the following. So we start with n triangles. Each triangle is oriented, and we assume that n is even. The number of triangles is even. It's a technical assumption, it's important. And n is large, n tends to infinity. So once we have this n triangles, each triangle has 3 sides. So in total we have 3n edges, and we find a random pairing between these 3n edges. So here we use our assumption that n is even, so 3n is an even number, so we can split it into pairs. And once we pair 2 sides, we glue the corresponding triangles along those 2 sides such that these orientations are opposite. So once we glue this, this gluing is done on all edges, so we obtain a closed orientable surface. So once pairing is fixed, we glue these pairs of edges, we obtain a closed orientable surface. And this surface will be random, and this randomness comes in because we have a random choice of pairing. The pairing, the way we pair the sides, is random.
how do you pair the pairs? So first you have n of them. You say n is 10. Now you have 5 pairs. And what do you do with these 5 pairs?
You glue them together. So if you, okay, so I'll just explain in maybe let's go to the next slide and then come back if necessary. All right? So, so how to pair 3n edges? 3n edges. So we can take, let's label them 1, 2, 3, 3n, and then make a random permutation of this 3n edges. So the number of permutations is 3n factorial. Okay. And then we can pair the first and the second, the third and the fourth, the fifth and the sixth, and so on. So we obtain a pairing. And this pairing depends on this random permutation which we started with. So, but for us, I mean, what is important is which side is paired to which. So we divide this, I mean, in each pair we can switch the order of these two sides. We can swap who was the first, who was the second. This gives this factor. And also you can permute the pairs between themselves. This gives you this factor. So the total number of pairings is this number, 3n factorial divided by these two numbers, which you can check is this product of all odd numbers from 1 to 3n minus 1.
So your surface does not be connected?
Yes, sometimes, yes, that's right. That's right, but I will come to this. But it is very orientable.
Is it we have two edges of the same triangle?
Yeah, it's okay. It's all right. So the surface will be orientable, but it may not be connected. It may be disconnected, clearly. So, so let's denote by h of sigma, denote the number of vertices of the obtained surface. This number depends on how you glue the edges. So it is a random variable. And now, knowing this h, we can compute the Euler characteristic. H will be the number of vertices, the number of sides will be 3n over 2, and the number of triangles is n. So you see that Euler characteristic will be h minus n over 2. And now, this is one of the results of Pippinger and Schleich. They showed that with probability of the 1 minus, well, essentially going to 1, for large n it goes to 1, with probability tending to 1, the surface is connected. So of course it may be disconnected, the probability that it happens goes to 0 for large n. And then if it is connected, then we compute the genus out of this Euler characteristic. So the genus will be n over 4. This will be essential, well, the biggest factor, the biggest summand will be n over 4, plus 1 n minus h over 2. And so we need to know, h is random, so we need to know expectation of h. So they proved in this paper that expected genus will be n over 4 minus half log n plus unbounded quantity. So this is, I mean, of course there are more results in this regarding this model, but I don't want to go further. So what I just want to say is that this is the first example of a large random space. So here we have n is large, n goes to infinity. Many choices is choices which side edges we pair to each other, and the result is kind of predictable. Of course, there is this expectation of the genus, but there are also variants of this genus. So there are many precise results about these random surfaces, and it's quite an interesting and still developing subject. So this next model, these are random 3 manifolds. This was developed by Dunfield and Thurston, and you can see that it is the same year. I mean, there is a big random, but there is no randomness with the year. Year is the same, 2006. You will see that it will repeat again this year. So this three manifolds of Dunfield-Thurston, they are different from random surfaces. You could have said, I mean, we can say, let's take n tetrahedra and oriented tetrahedra and pair at random their sides and do the gluing, and we will obtain a random three manifold. But this will not work. I mean, this works only for surfaces. For three manifolds, you will get a closed manifold with singularities. So the singularities will be of type high genus surface and conoid. So there will be points which have link high genus surface and not a sphere. So there will be singular three manifolds. So they, Dunfield and Thurston, they looked at a different model, which is the following. So we fix a genus G. We fix a handled body of genus G, which looks like this, with G holes. And we look at the boundary of this handled body, which is a surface, closed surface of genus G. And now we want to produce a closed three manifold as follows. So we take two copies of such handled bodies. We take two handled bodies and we glue their boundaries via a homeomorphism H. So this three manifold will be the union of two handled bodies glued along H. And randomness here comes through this H. This homeomorphism is chosen at random. It will be on the next slide. So this is called Higard decomposition, and it is known that any three manifold can be represented this way with some H. So now how to choose this H? So the genus is fixed, and if we denote by Mg the mapping class group of the surface, so it's a group of homeomorphisms of the surface up to isotopy. This group is very well known, and there is a very explicit description of this group in terms of generators and relations. So if we fix a set of generators for this group, then we can generate a random element as a random word of some length L in this generator. So we just randomly write a word in the set of generators of length L, and this defines a homeomorphism H. And then once H is defined, we produce this closed three manifold depending on H, where H is a gluing homeomorphism. And then, I mean, to make this model work, Dunfield and Thurston, they assume that this L, the length of the word, goes to infinity. So this is the second model, which is very interesting. I will not go into further into this model because we have time limitations. So I have said already this. So the next model. So we started with random surfaces. They were manifolds of dimension 2. So then we looked at random three-dimensional manifolds, and this will be a random closed manifolds of high dimension, of dimension going to infinity. And they come quite naturally as polygon spaces. So here we start as follows. So we fix some vector L with positive real numbers as coordinates, Li. And we consider planar n-gons, so n-gons like this on the plane, such that the first side has length L1, the second side has length L2, L3, L4, and so on. And we our objects are shapes of these n-gons. So the length is fixed, but the shape you can vary. I mean, the shape can vary, and in this picture you can see two shapes, and if you take this diagonal and reflect this triangle with respect to this diagonal, you get this shape. So you can see that these are two shapes with the same sides. So our object now is a variety of shapes with fixed L. So formally we can describe this variety of shapes as what is called here ML. So these are unit vectors, U1, UN, unit vectors on the plane, such that if you make, such that the sum is 0, this means that if you, so U1 is the direction of the first side, U2 will be direction of the second side, and so on. So these are directions of the sides, and this condition means that if you follow this rule, you will come back. So it will create a closed n-gon. And now we quotient with respect to the rotation group of the plane, so because we want to study shapes and not the way they are placed on the plane, so we quotient with respect to SO2. So this is our object, ML. Let's just read this sentence here. It is a theorem, but we will not do any proofs here. So if this length vector, this is called length vector. If this vector is generic, then this ML is a closed smooth manifold of dimension n-3. Let's just skip what it means generic. It doesn't matter for now. Let's look at examples. So if n equals 3, we are dealing with triangles on the plane. And triangles on the plane, it is school material, right? We know from the school geometry, we know that a triangle is given by side lengths. But here we are not allowed to do reflections. I mean, we quotient, just want to show you back. See here we quotient with respect to SO2, not with respect to O2. So reflections are not allowed. So as a result of this, we see that for n equals 3, this ML is a two-point set when you have two triangles, triangle 1 and its reflection. Or it can be empty set. Empty set is when you cannot make a triangle out of these three lengths. For n equals 4, this variety ML can be either a circle or two circles, I mean disjoint union of two circles, or an empty set. So an empty set happens when one side is so large, so long that you cannot form a closed link. Maybe if you I just want to show you this. When do we have S1 two circles? So if I take a triangle and one side very little, so this in this case, I mean, this triangle has two positions, this one and reflected one, and this small side can kind of rotate like a little bicycle there. So this creates a circle. So this, so in this case, you have disjoint union of two circles. Okay. For n equals 5, this ML is a surface. I mean, in general, it has dimension n minus 3. So if n is 5, it is two-dimensional. So it's a closed surface, orientable surface, and it can be one of these 7 surfaces. So empty set, 2 tori, and a closed surface of genus 0, 1, 2, 3, 4. And here, I mean, there's people who initiated the theory and made very important contributions. Kevin Walker, Misha Kopovich, John Milson, and others. So let's go to the next slide. So what happens when n is large? Well, this table is taken from a paper by Hausman and Rodriguez, and it shows the numbers. The Cn is the number of different manifolds which you obtain varying L. Fixed n, but you take different vectors L, how many different manifolds you can obtain. For n equals 3, we had 2 options, as a circle and an empty set. For n equals 4, we had 3 options, 1 circle, 2 circles, and the empty set. For n equals 5, we had 7 options, which we just discussed. And if you go further, you see that for n equals 10, there are 52 million different manifolds. So the number of manifolds you obtain grows very fast. So what happens when n tends to infinity? If n goes to infinity, I mean, we can say we take this simplex, we have this simplex of where vector L is selected, and we pick this L at random. We put some probability measure on this simplex, and we sample L at random with respect to a probability measure. Then once L is selected, we obtain ML, which is a random manifold, dimension n minus 3. So, so what happens when n goes to infinity? So the result which, well, we will look at the Betti numbers. We look at the Betti numbers of these manifolds. We fix P, so we fix this P. P is a dimension, I fix P, let's say 5. I look at 5-dimensional Betti number of this random manifold, and it will be a random function on this simplex, and the expectation is given by this formula, so this is a measure. So this is a measure which we have to choose before we can do anything. So it is a selected measure on the simplex. So the result which I state here as in a very vague form, it is intentionally vague form. I mean, it's a mixture of different theorems obtained by Kapeler, Dombry, Mazza, and myself in different papers. And it says, again, very vaguely, it says that for a vast class of probability measures, mu n, the expectation of this Betti number is this binomial coefficient up to an exponentially small error. So, I mean, for me, this was kind of first time when I was shocked by the stochastic topology. For me, this was really shocking because, you see, the result is that this expectation, in fact, it does not depend on the measure. So for large n, if n is large, the expectation is this binomial coefficient, this integer, and this error is exponentially small. So for large n, this error will be, I mean, it goes to 0 very quickly. And the meaning of this binomial coefficient is it is a Betti number of, at this degree, this dimension, of linkage of the configuration space of a linkage where all the bars are equal. It's called equilateral linkage. I just want to, 1 second. There is one file which I, oh, here. Okay, sorry. Oh, yeah. I lost it anyway. Oh, yeah, this one. So, just to, is it time to make a break, more or less? 5 minutes? Yeah. Okay, so, oh, sorry. I missed it again. What was this? Okay. So this is DNA, a molecule, and you can see it is it's a graph. I mean, it's not as simple as this chains which we considered before, but it is it consists of different parts which look like chains, and it is a large molecule, large that there are many very little elements, very little bars forming this molecule. So if we are looking at the configuration space, it will be a huge manifold of huge dimension. How to deal with this manifold, how to represent this manifold, well, it's all questionable, because, I mean, you cannot assume that it is deterministic. You should assume that it is random. And so this result of the previous slide, which kind of philosophically may be interesting, that the Betti numbers asymptotically are exactly the same as if we assume that all sides are equal. So maybe this principle can be also applied for more complicated situation like this to describe the configuration spaces of these molecules. So I still have a few minutes before break. Or?
It's okay.
Yeah.
Either break now or 3
Let's make a few more minutes. So this next subject is a classical. It's really good, I mean, to relax before the break. So it's random Erdős-Rényi graphs, and I think it was mentioned here many times in different talks. So it's also an important example of large random spaces. So here we have 2 parameters, n, an integer, and p, a real number in the interval 0, 1. And we consider the set of all graphs, which is denoted by G and P, on n vertices, which are labeled by integers 1 to n, where each edge, ij, is included at random, independently of all other edges, with probability p. So this is a typical example of a large random space. Each edge is a random variable, and different edges are independent. A probability function on this space, well, we can write it in this formula. So p to power f1 of gamma, it is a number of edges of gamma, times 1 minus p, and this n choose 2 minus f1 of gamma. So this difference is the number of edges which are not included in gamma. So this is a classical model from Erdős-Rényi from 1960, and one of their most important theorems says that the following: it describes connectivity of a random graph. So if omega is an arbitrary sequence of real numbers tending to infinity, then for p greater than log n plus omega over n, the random graph is connected asymptotically almost surely. So this is an important word which I'll explain in a moment. And if p is less than log n minus omega over n, then a random graph is disconnected asymptotically almost surely. So asymptotically almost surely means that probability that this statement holds tends to 1 as n goes to infinity. I think this would be the right place to make a break. Thank you. Continue. So the next model I want to discuss was also published in the same year, 2006, by Linial-Meshulam, and Erdős-Rényi is here. So they started a topological study of random simplicial complexes. The first paper was about two-dimensional complexes, and then there were papers about higher-dimensional complexes, but I'll discuss two-dimensional case. So the model which they considered is quite similar to the Erdős-Rényi model, but everything in one dimension higher. So here one starts with a complete graph on n vertices. So we have n vertices, and every pair of vertices is connected by an edge. These vertices are labeled by integers 1 to n. And then we consider triangles. We decide which triangles we add, which triangles we don't add. So each triangle is a random variable. We include this triangle at random independently of the others with probability p. So p is a parameter which is fixed from the beginning. So we obtain a random simplicial complex of dimension 2. And of course we are interested in the behavior on the properties of this complex when n becomes large, when n goes to infinity. So the theorem, so maybe here we'll just look at the same model from a different point of view, how to describe it. So our probability space is denoted by y2 and p, and the Linial-Meshulam model, and it consists of all two-dimensional complexes which contain one skeleton of the simplex of dimension n minus 1 on n vertices. So it is a complete graph. This is a complete graph, and it is subcomplex of two skeletons of the simplex. And the probability function is given by this formula, which is very similar to the formula which we had before the break in the Erdős-Rényi model. So here f2 of y is the number of triangles in y, and this is the difference is the number of triangles which are not included into y. So the theorem which okay, so this again, this proper language which we use, asymptotically almost surely, means that the corresponding property holds with probability tending to 1 as n goes to infinity. And this language we use constantly. So the theorem which Linial-Meshulam proved in that paper is the following theorem, which looks very similar to the statement of Erdős-Rényi theorem about connectivity, but here it is not about connectivity. These complexes are a priori connected because the one skeleton is a complete graph. So the question is about vanishing of the first homology and non-vanishing of the first homology. So if we replace 1 by 0, this would be vanishing of 0 homology, which is exactly connectivity. So the theorem of Linial-Meshulam says that if p is greater than this threshold, which is 2 log n over plus omega over n. Then this random 2 complex has vanishing first homology with Z2 coefficients, asymptotically almost surely. So here we see 2, and in the case of Erdős-Rényi, there was no 2, so this is extra, the extra factor 2 here, but omega is similar to what was in Erdős-Rényi theorem. And the second statement says that if P is smaller than 2 log n minus omega over n, then the random complex has non-trivial first homology group. So we can think about the theorem as follows. So when what happens when we have P growing, when P is the probability of adding of a triangle. So if P is small, then we have in total quite a few triangles added to our simplicial complex. And initially, the simplicial complex, well, it consisted of a complete graph, and then we add to this complete graph certain number of triangles at random. So if P is small, which is smaller than this precise number, then it's still we have huge non-zero first homology group. But when P goes above this number, crosses this threshold, then we see that then all these cycles, one-dimensional cycles, have been killed, and we have trivial first homology group. So here this typical situation is called phase transition. When we cross certain value, the property of our complex changes dramatically from vanishing to non-vanishing. From non-vanishing to vanishing. For this talk, it will be convenient to assume that P, the probability parameter, has this form n to power minus alpha, where alpha is a constant real number. So then we can rephrase the theorem as follows. So if alpha is greater than 1, then H1 is non-zero. And if alpha is smaller than 1, the first homology group vanishes. So we should think that alpha, when alpha is large, when alpha goes to infinity, then P is small. P is n to power minus alpha. So for large alpha, P is small. So for large alpha, we still have cycles. But when we cross this one, then we kill. Maybe kill is too cruel. Should we say eliminate, or I don't know. What was the word? I don't know. Clear. We clear all cycles. Exactly. Yeah. Yes. Okay. So this is this picture shows the theorem. What about the fundamental group? So these are two-dimensional complexes. See, graphs are very simple topologically, but two-dimensional complexes are very complicated objects. So they have fundamental groups, for example, and fundamental groups are, well, general groups. Any group can be fundamental group of a two-complex, any finitely presented group. So it's a huge variety of groups, and these are random groups, groups of random two-dimensional simplicial complexes. So this a significant result of Babson, Hoffman, and Kell says that for alpha, maybe I should start with this part. So the fundamental group is non-trivial when alpha is between infinity and 1/2, but when we cross 1/2, it becomes trivial. Moreover, when it is non-trivial, in this region, when it is not trivial, it is hyperbolic in the sense of Gromov. So the hyperbolicity I will explain a bit later. It will be a slide on this. So this picture again illustrates the theorem of Babson-Hoffmann-Kell. So it shows that there's 1/2, this threshold. So fundamental group is non-trivial here. So again, alpha goes from infinity to 0. When alpha is at infinity, we are close to the complete graph. Fundamental group is not trivial. And then when we cross 1/2, the fundamental group becomes trivial. So we see that the threshold for vanishing of the fundamental group is different from the threshold for vanishing of the first homology. So the first homology vanishes at 1 when we cross 1, and the fundamental group becomes trivial after we cross 1/2. So this means that if we are in this region between 1 and 1/2, we have our random group is non-trivial random perfect group. Perfect means it has trivial abelianization. It has trivial abelianization, which is a bit surprising. So actually, I just want to say that in many instances, in the stochastic topology, if something happens, it happens for very simple reason. There's a kind of general principle that if something is true in stochastic topology, it's true for some simple reason. But it's not true in general. For example, here, it is one of the instances when it is not true. It is not, the appearance of a non-trivial random perfect group is not an obvious thing. Another theorem, the two theorems here, first says that the fundamental group in this area, the fundamental group is free. But when we cross this one, the fundamental group has property T. So this was proved by Kell, and this was proven by Cohen, Costa, Kapiller, and myself. So, from this point of view, there is another surprise. So you can see that the fundamental group of random two-dimensional complex can be either free or has property T. So property T is Kazhdan invented this property T of Kazhdan. So this means that the trivial representation is isolated in the space of all representations. So you cannot deform the trivial representation to non-trivial. So no, Dan Cohen, yeah. There are many coins. Yes. So it's a bit surprising that I'm getting kind of two options, either free or property T, and there is nothing in between. For example, Z plus Z, group like this, Z plus Z, it is not free and it has no property T, so it doesn't occur. It occurs with probability tending to 0. Torsion in the fundamental group. Well, it's our work with Costa, Armindo Costa here. So we proved that if alpha goes to until 3/5, then there is no torsion. In this area, there is no torsion in the fundamental group. Between 3/5 and 1/2, the fundamental group has two torsion with probability 1. So two torsion appears. However, if we look at, maybe I'll skip this. Sorry. Okay, I'll come back later to whatever. So, this is a real projective plane. This is a triangulation of the real projective plane. It's a minimal possible triangulation. So we have a hexagon here, has 6 vertices, but opposites should be identified, 2 and 2, 3 and 3. So there are 3 vertices inside, in the interior, and there will be 3 vertices outside. So it's a projective plane, a real projective plane with 6 vertices, and it has 10 triangles. So 10 triangles, and 6 over 10 is 3 over 5, and this is this 3 over 5 here. So this explains this number, 3 over 5. So this real projective plane embeds into a random complex such that the inclusion induces a monomorphism on the fundamental groups. And this is how we show the existence of 2 torsion. The proof of this results uses the uniform hyperbolicity of, the uniform hyperbolicity of random simplicial complexes and some other techniques which I will skip for now. And this hyperbolicity, we should look at it. So what is uniform hyperbolicity? So we look at a simplicial complex, and we look at simplicial loops. So this is a circle, and this is one skeleton of X. So we look at simplicial null homotopic loops, so loops which you can construct in X. For each such loop, this absolute value of gamma is the length of gamma. It's the number of edges which are in the subdivision of the circle. And A of gamma is the area of gamma, so it's a number of triangles in the minimal spanning disk for gamma. So let me explain. So this gamma is a loop in X, and it is null homotopic, so you can find a 2-dimensional disk which bounds this loop. And this disk you can also make simplicial. You can subdivide. So we take the minimal disk, minimal in the sense of it has smallest possible number of triangles. The smallest possible number of triangles which you can use, which you can triangulate 2-dimensional disk to show that gamma is null homotopic. So this is area. This is called area of gamma. So now we look at the number which is called the isoparametric constant. So we look at a ratio between the length of the loop and the area. And this we take over all null homotopic loops in X. So we take inf here, so we take a smallest ratio between the length and the area. So we want to avoid the situation when a short loop bounds a very big minimal disk. So we want to avoid situation when to show that a loop is null homotopic, you need to produce a very large disk. And this is captured in this ratio between length of gamma and the area of gamma. This is called the isoparametric constant. So there are 2 possibilities here. So this inf can be 0. So it is infimum of infinite set of positive numbers. So this infimum can be 0, or it can be positive. So if it is positive, then this property actually depends only on the group. And then we say that this group is hyperbolic in the sense of Gromov. And then this is equivalent to the statement that in this group there is a linear isoparametric inequality, which is not on my slide. So which says that this A of gamma, area of gamma, area of gamma is bounded by a linear function of the length. It's less or equal than some constant times the length. So this is hyperbolicity in the sense of Gromov. And And the theorem about uniform hyperbolicity of random complexes says that if we are in this range, where alpha is greater than 1/2, so this is the range where the fundamental group is non-trivial, then there exists a constant such that with probability tending to 1, as n goes to infinity, a random complex y in the Linial-Meshulam model has the following property, that any subcomplex has this isoparametric constant bounded by C alpha. And the C alpha is the same for all subcomplexes. So this constant depends only on alpha, on this exponent. In particular, the fundamental group is hyperbolic. But this is very small part of this statement. I mean, this uniform hyperbolicity is a very strong property which we used many times. Okay. So I just want to skip something. I want to skip something to get to the Whitehead conjecture. I'll just skip this. Yeah, maybe let's look at this theorem also. It's just one theorem. So this theorem also may look a little bit surprising. So this theorem says that if we take some odd prime p. So we saw earlier, we saw that there is a range when the fundamental group has 2 torsion. So we can ask, what about 3 torsion, or 5 torsion, or some odd torsion? And this theorem answers this question. So this theorem says that for any odd prime m, let's say m equals 3, and for any alpha except 1/2, where we don't know what happens, the fundamental group of this random 2 complex, so this should be minus here, this should be minus alpha, has no m torsion, asymptotically almost surely. So this, so there is no odd torsion, in other words, except that, I mean, at the same time it has 2 torsion, but it cannot have 3 torsion, which is surprising. Okay, so now I come to this Whitehead conjecture. And this is a deterministic question, which is still open, and it is the following. So it was raised by Henry Whitehead in 1940-something, 1940s. So it says the following. So first we need to define what is aspherical, what it means aspherical. So we look at a 2-dimensional finite simplicial complex. We say it is aspherical if the second homotopy group of X is 0. And equivalently, X is aspherical if the universal cover is contractible. This is equivalent for 2-dimensional complexes. And if you look at surfaces, every orientable surface of genus except 0, the sphere is not spherical, but all other orientable surfaces are spherical. And non-orientable surfaces also are all spherical except the real projective plane. Okay, so this is here. So what is the question? In 41, Whitehead suggested the following question. Is every subcomplex of an spherical 2 complex also spherical? So it's a very simple question. And it's still open. And it is known as the Whitehead conjecture. And I think there were people, some people worked very hard on this conjecture, in particular in Germany, several people I know. So it was attempted by many people over many years, and still the answer is not known, but there are many results in confirming this conjecture under extra conditions, under additional assumptions. So we want to use probabilistic technique to tackle this conjecture, Whitehead conjecture. So this can be done as follows. So what if we produce a spherical two complexes randomly? What if we can make a random model, probabilistic model, producing a spherical two complexes? And what if we estimate the probability that the Whitehead conjecture is satisfied? So if we can do this, and if we make this estimate and suppose it turns out that this probability that the Whitehead conjecture is satisfied is less than 1, this would imply that there is something where it is not satisfied. So there will be a counterexample. Okay, so now if we look at this Linial-Meshulam model, or this random simplicial complexes in this model, they are not as spherical. They are absolutely not spherical. So we cannot say that we can take this model and apply this program and try this program on this model. But what we can do, we can take this random complex y and then look at subcomplexes of y which are spherical. And in fact, any finite subcomplex can be realized as a subcomplex of a random y. So we don't lose much this way. So this theorem tells us the following. So if we are in the Linial-Meshulam model with p n, n to power minus alpha, where alpha is greater than 1/2. So again, this range where the fundamental group is non-trivial. Then with probability tending to 1, as n goes to infinity, this y, this random complex, has the following property. A subcomplex of y is a spherical if and only if, well, maybe I'll just, instead of saying this, I'll just say it in simple words. I'll say a subcomplex is a spherical if and only if it has no small bubbles, small pieces which it shouldn't have if it is a spherical. More precisely, this is written here. So a subcomplex is a spherical if and only if any subcomplex of this y prime with z many, with at most z many faces, this epsilon is this number which is fixed, which is given. It depends on alpha only. It depends on this alpha. Where any subcomplex of y prime with at most that many faces is a spherical. So to check a sphericity, you need to look only at small subcomplexes and decide if they are all spherical or not. So this is our theorem with Armindo Costa here. And as a corollary of this theorem, it follows that under the same assumptions as before, there's alpha greater than 1/2, any spherical subcomplex satisfies the Whitehead conjecture, which means that all subcomplexes of y prime are also spherical. So this follows automatically from the previous theorem, because if y prime is spherical, this means that it doesn't have small pieces which are forbidden by that theorem, so that every subcomplex also has no these small pieces. So unfortunately, we see that this result says roughly that with probability tending 1 to 1, the Whitehead conjecture should be true. So it does not prove the Whitehead conjecture, it does not disprove the Whitehead conjecture. Deterministic Whitehead conjecture. So, there's young people who are here, maybe, well, some of them may try this. It would be nice to, there is a possibility that using this deterministic result, one can show that a deterministic Whitehead conjecture is true by looking at, roughly as follows. So if there was a counterexample to the Whitehead conjecture, then possibly there would be many counterexamples like this. And if you estimate how many and how big will be the variety of counterexamples and sum up the probabilities, if it happens to be positive in this measure, in this probability measure, this would imply that that would prove the deterministic conjecture. I think I will finish for now. I mean, this is the last talk, so I should say thank you to all our participants who came patiently listen to our lectures. Thank you very much. And also we should thank the Hausdorff Institute for providing these facilities for us and inviting all of us here. And you want?
Let me add a few words.
Sure.
So first of all, thank you for all of you for participating here. I hope you had a nice stay here. I hope you learned a lot through the talks that have been given and through the discussions we had. I hope you have made a lot of new connections, because that's maybe in the end the most important effect of such a spring school. And then I think we should give an applause to all the speakers who have made a big effort at various levels. I'm sure you have seen that, but everybody has made a big effort to show you the vast area that it has become, the vast area of applied and